Well, we're really flying through our logarithm chapter, and we are all ready to start solving equations that involve logs, and we're going to use a lot of the properties that we've learned over the last 2 days and kind of combine them all together in one big day today. And our two monster steps are, number one, we want to make sure that we're able to isolate the term that contains the logarithmic expression. So, in other words, isolate the logarithmic term. And that really, you'll notice that's a theme through a lot of the year, whether it was radical equations or absolute value equations or whatever type of equation we were working with, it involved isolating some special component within that equation. And then the second thing, once we get that log term isolated, we're going to convert it to exponential form. So we're going to convert the logarithmic equation into an equivalent exponential. And I'm going to run out of room and I'll spell it the best I can. Exponential equation. All right? So before we dive into our first one, why don't we just review how to convert from logarithmic to exponential form? And we're just going to refresh our memory on our little phrase around the world and how we do that. So let's imagine that we said y equals log base b of x. And we wanted to convert it. And I like to use the double arrow for a conversion. We're going to say b raised to the y power equals x. And that's how we'll convert it. We'll say b raised to the y equals x. These two equations are equivalent. It just happens to be that one of them's in exponential form and one of them's in logarithmic form. We've been preaching throughout this chapter that it's like saying the same sentence but in two different languages. So our directions were very friendly here. They said, okay, we are going to solve the logarithmic equation and by first isolating if necessary and then rewriting it in equivalent exponential form. So they kind of helped us out. They told us those first two steps. This one is completely isolated already. So I'm just going to say 6 raised to the second power equals x. And bada boom, x equals 36. And again, what was the domain of this function before we even started? We would have said all x values greater than 0. Does 36 satisfy the domain? Yes, it does. So that is a solution. All right, again, this logarithmic term is already isolated, so we can go ahead and just convert it. We could say 2 raised to the third power equals the quantity x plus 5. And let's see, 2 to the third power is really 8. So then we just subtract the 5 over, and we could say 3 equals x. What was the domain? Well, we knew that this function right here, we could say x plus 5 had to be greater than 0. In other words, x had to be greater than -5. Does the 3 satisfy that? Yes, it does. So we'll say he is indeed a solution. Our third example is the first one where we really have to do any work to get it isolated. And what I want you to do is I want you to kind of visualize, let's see, and we can kind of do a dotted box around this portion right here. This is the part that I want to try to isolate. So essentially, before I get it isolated, I'm going to have to add this 2 over to both sides. Notice I'm moving the 2 before I worry about the 3. So I've got 3 times the log base 5 of 4x plus 1 equals 6. And then we'll divide both sides of the equation by 3 so that those numbers cancel. And we get log base 5 of the quantity 4x plus 1 equals 2. All right, now that we've got it isolated, we can go ahead and convert it. We could say 4 raised to the second equals the quantity 4x plus 1. Let's see, so we got 16 equals 4x plus 1. And then from here, it's very nice, simple, linear equation. We'll subtract the 1 over, and then we'll divide both sides by 4, and we'll get 15/4, which is equivalent to about 3.75. Let's go check the domain really quick on that original function. We could say that the inner function, 4x plus 1, had to be greater than 0. 4x is greater than -1, x is greater than -1/4. So indeed, our solution to 3.75 is greater than -1/4, and it's acceptable. Well, so far, our first 3 examples had only, and I say only, one log term in the entire equation, and therefore they were relatively easy to isolate. All right. So everything up till now has been relatively easy by comparison anyway. And so now we're going to start to see examples like the one that I've imported here at the top where there are multiple terms that contain a log. So we've got one term here minus a second term there. They both have a log. So what do we do when we have multiple logs within the equation? Well, let's see here. When we have two or more logarithms that are involved, we have to combine, or another word that I used a lot in last night's video was the word condense these logs using our laws from yesterday. We were going to use either the product or the quotient or the power rule. Okay, so hopefully remember the product and the quotient and the power rule for power laws from yesterday. And those are the ones we're going to use. Okay, so as we look at our first example here, we see that we do have multiple terms that contain a log, so I'm going to have to combine or condense those two terms first. And I'm going to use, because of the minus sign, and I know that subtraction is linked together with division, I'm going to use my quotient rule. Alright, what I need you to make sure we do is when we condense, we're condensing it into one log term. We're only going to write the word log once. Tell yourself you're not allowed to write the word log more than once. It's going to be the quantity 3x plus 23 divided by the quantity x plus 1. I know that looks messy, but it's not as bad as you think. Now that we've combined them, it's basically just like the first three examples where we're going to go around the world. We're going to convert this to exponential. We're going to say 2 raised to the third power equals the very ugly quantity 3x plus 23 divided by x plus 1. Now, of course, 2 to the third is really an 8, so let's just go ahead. We're going to cross multiply and make sure we distribute the 8 all the way through the quantity x plus 1 right here. So we get 8x plus 8 equals 3x plus 23. And what's that going to give us? Let's see, subtract 3x from both sides. That'll give me 5x plus 8 equals 23. Subtract the 8 over, that'll give me 15. X equals 3. And I'm just going to go back up here and make sure that 3 works with the domain. If we plug a 3 into this expression, 3 times 3 is 9. I got a 32, and because that's greater than 0, it's acceptable. If I plug the 3 in there, I got a 4, and that's greater than 0. So again, it's acceptable. We are good to go. All right, let's go try part B here right next to me. Now again, we see the multiple terms, so we're going to have to condense them, and we see a plus sign. So I'm going to write down the product rule. And when we condense, what are we allowed to do? We're only allowed to write the word log one time. It's going to be logged, and it's going to be x times the quantity x minus 3, because addition is linked with multiplication. I know I have a base 10, so let's say, go around the world, 10 raised to the first power equals the quantity x times x minus 3. Let's say 10 equals x squared minus 3x. It's a quadratic, so let's go ahead and we'll try to buzz through this as fast as we can. Make sure we get 0. We're getting a little sloppy there. Sometimes on our quizzes and our homeworks, we're not putting the 0 in there. Factors very nicely. So I'm getting solutions of x equals 5 and x equals negative 2. Let's go check both of them, see if they satisfy the domains. This domain right here, we would say that x has to be greater than 0. Therefore, we're going to have to reject the negative 2. This domain, we would say x has got to be greater than 3. So let's go see if we can keep either one. It does look like the 5 satisfies both domains, but the negative 2 doesn't. So we'll say 5 only. Alright, we're going to see a little feistier example here. And the first thing I want you to say to yourself, well, when they ask for an intersection point, we're going to just set the equations equal to each other. Okay, set the equations equal. So, or in other words, you could think of it as the substitution method as well. You know, we're going to take this quantity right here and substitute it in for y so that it says the log base 3 of x plus 25 plus 3 equals log base 3 of x plus 1 plus 5. All right, now, great time, great opportunity to maybe hit that pause button and try to solve this one on your own. I know it's a little bit harder than the last couple we've seen, but nonetheless, the first thing I'm going to do is I could go ahead and subtract the 3 from both sides. Also, what I'm going to do is I'm going to try to group all of the logs over together on the opposite side, over on the left side. So I'm going to subtract this log from both sides. It's going to look really funny. We're kind of killing two birds with one stone here, so to speak. And now, these two terms are not like terms because they have different inner functions. So I cannot combine them together yet. I just have to list them separately. So I'm going to say log base 3 of x plus 25 minus log base 3 of x plus 1 equals, and then when I subtracted the 3 from the 5, I got a 2. So just a quick recap, what did I do? I grouped all of the terms with a log in them on the left side, and then all the terms that didn't have a log went to the right side over here. Okay, now, we do have the multiple terms with the log, so I'm going to condense them into one term. You're only allowed to write the word log one time. I'm using the quotient rule. Quotient law. Now, if you haven't tried it on your own yet, now I think you really can try it on your own. Go ahead and you go around the world and convert it to exponential, and then just go ahead and get rid of me and try this one all on your own. Okay, I'm distributing the 9. Going to subtract an x from both sides, and then I'm going to subtract a 9 from both sides, and that's going to give me 16. Therefore, x equals 2. Let's go check the domains real quick. Let's see. The domain here was all x is greater than negative 25, and this domain was all x is greater than negative 1. So I believe our solution does indeed satisfy those domains. All right, totally switching gears here to a new topic, and I think the word's going to jump right out at you. When you read the directions here, what's the one word that jumps out at you? Hopefully it's the word inverse. So we're going to go ahead and we are going to switch x and y right away. And so I'm going to rewrite this equation. I'm going to say x equals log base 5 of the quantity y plus 6 minus 2. Okay, now somehow we got to get this y by itself. So the first thing I'm going to do is I'm going to add 2 to both sides. And I'm going to say x plus 2 equals log base 5 of the quantity y plus 6. Now, I'm not allowed to subtract the 6 yet because it's trapped within those parentheses. So what I'm going to do now is I'm going to go around the world. I'm going to convert to exponential. I'm going to say 5 raised to the power of x plus 2 equals the quantity y plus 6. Here's what it would look like. 5 raised to the power of x plus 2 equals the quantity y plus 6. Now just subtract the 6 over now. Make sure it's not part of the exponent, and you've got yourself a beautiful inverse equation. Now remember, you were expecting an exponential because it was guaranteed that if you start with a log, the inverse will be an exponential. All right, let's try the second one again. What's the base? I don't see a base. It's invisible, right? There's an invisible base 10 right there. So anyway, let's subtract the 5 from both sides. Oh my gosh. You should be screaming at me. What did I forget? I forgot to switch the variables. X equals log base 10, that's optional, 2y minus 1 quantity plus 5. Okay, now let's subtract the 5 from both sides. So we got log base 10 on quantity 2y minus 1. Again, tell yourself we're not allowed to add 1 over because it's trapped within these parentheses. So I'm going to convert it to exponential. And I'm going to grab a blue color here. Let's go 10 raised to the power of x minus 5 equals the quantity 2y minus 1. 10 raised to the x minus 5 equals 2y minus 1. Let's go ahead and add the 1 over. Just a ton of algebra tonight. Just a lot of great review. We're becoming so strong in this category. And then I'm going to divide the entire equation on both sides by 2, and we're not allowed to simplify. The reason we're not allowed to divide the 10 by the 2 is because the 10 has this special power, and since the 2 doesn't have the same exponent, we're not allowed to divide them. This is your final answer right here. Algebraically just means we're not allowed to graph it. And we want to find the x-intercept. So anytime you want to find an x-intercept of any function, what you're going to do is you're going to substitute a 0 in for y. And so that's what I'm going to do. I'm going to say 0 equals log base 2 of the quantity x minus 7. I think once we did this, you guys are certainly capable of solving this one on your own. We're going to add the 4 over. In other words, we are isolating the logarithmic expression. Now I'm going to convert it. I'm going to go around the world. I'm going to say 2 raised to the 4th equals x minus 7. 16 equals x minus 7. And therefore, x has to equal 23. That would be your x-intercept if you graphed this function right here. Well, I'll tell you what, for our last couple of examples tonight, we got a totally new ball game. All right, and what's so radically different about these is that we've got logs on both sides. So let's put a big note in our notebook here. We've got logs on both sides of the equation, and that's really the first time tonight that this has happened. And so what we're going to do is really just 2 steps. What I'm going to do is I'm going to combine or condense these 2 terms into one term first. All right, we're going to condense, and then what we're going to do is we're going to just clear all the logs, and this is a special trick that we can use if we have logs on both sides. But anyway, the condensing would be the product law because of the plus sign we see. So I'm going to only allowed to write the word log 1 time on this side of the equation, and it would be x times 9, which is 9x. Now, similar to what we did when we were solving exponential equations with the same base, we can go ahead and clear those logs, and we could say that 9x is simply equal to 45, x must be equal to 5. So condense and clear is our motto. Let's go ahead and condense these. We're going to use the quotient. Always, I think it's helpful to kind of talk our way through it and identify the law we're using. Log base 10 of the quantity 2x plus 1 divided by 3 equals the log of 5. So how many logs do you have on each side? We've got just 1, so we can go ahead and clear them out. And we'll say the 2x plus 1 over 3 equals 5. Cross multiply. Then we're going to subtract 1 and divide by 2, and we're going to get x equals 7, and it certainly satisfies the domain. So there's my solution. So basically, let's summarize that. What do I do if I have logs on both sides? Step number 1, condense each side as necessary. In ours, it was only necessary to condense one of the sides. We didn't have to worry about the other side because there's only one log over there. And number 2, we're going to then clear all the logs. All right, clear all the logs and just set their inner functions equal to each other. All right, our very last one tonight is by far the most challenging one. We're going to sprinkle in a few new tricks and take some monster notes here. Do you see this coefficient right here? That's probably the number one thing that I want you to see. And when you see that coefficient, what you're going to tell yourself is we have to use the power rule right away. All right, we have to use the power rule or the power law, whatever you want to call it. Now remember, the coefficient can travel back to the exponent, and I'm going to rewrite that first term as log base 4 of x squared. All right, so non-negotiable, we are going to have to use the power rule first, and that's every time you see a coefficient sitting in front of that log right there. Now I'm going to use the quotient law to combine these 2 terms, and it's going to be log base 4 of x squared divided by 2 equals log base 4 of 18. Now here's the good news. We've got logs on both sides of the equation, so I can go ahead and I can clear these logs. Again, they had to be the same base, but that'll always be true. That's not something we're going to have to watch out for or really worry about. I'll just tell you that straight up. Cross multiply, we get x squared equals 36. Take the square root of both sides. I'm thinking plus or minus 6. Now let's go up and see if they're both acceptable. I did have a domain right here where we would have said x has to be greater than 0. So I'm going to have to go down and reject the negative 6. Whoops. Reject the negative 6, and my only solution is positive 6. Okay? So really, the one thing I want you to really walk in tomorrow feeling good about is identifying that coefficient right here and using the power rule to move it to the exponent. All right, good luck tomorrow.